Students, now welcome back to this second part of this lecture, and here we are talking about most of the things about hierarchical clustering. So, please keep your attention on this. So far we have discussed about k-means clustering, and these are nothing but centroid approaches. We guess the central point first. In all this k-means clustering, whatever we discussed in the blackboard, in the whiteboard as well as here, is basically it assumes the centroid of each clusters. That is the key problem of this. So, then assign the point to the cluster based on the nearest neighbor distances. Now, in case of hierarchical approaches, we begin assuming that each point is a cluster itself. Why do you do that? And this mainly because we do not want to pre-assign or guess number of clusters at the beginning. So, after we assume every point is a cluster by itself, we repeatedly merge the nearby clusters using some measure of how close these clusters are. It can be again distance, or how good a cluster is, resulting cluster, how good a cluster the resulting groups would be, or average distance. Actually that is nothing but average distance. So, finally we apply the centroid concept, but we have no assumptions at the beginning. So, in k-means algorithm we choose the k cluster centroid first, we pick that and assign point to the cluster by picking these distances. Like here, suppose you have k is 2 and you have to assign 1, 2, 3, 4, 5 in that order, that is what it is. So, then you decide there will be 2 clusters k. So, what do? We have one cluster here, same thing here. So, you can see here we have designed one cluster there at the beginning. Then what happened? Then you measure this, put these centers, one center here, measure distance from 1 and 3 and they become one cluster, and then you can put another points here and see 2 and 4 are belong to the clusters. Instead of that, if you have k is 2, then you can put this centroid here and you can see the distance will be similar. Then you have 2 clusters, but assuming that may be wrong, because you can clearly see there are 3 clusters here. That is the problem of k-means clustering. So, k-means clustering performs this best if the data are well separated. When data points are overlapped, this clustering is not suitable, and it is faster as compared to other clustering. It provides strong coupling between the data points, and k-means cluster do not provide any clear information regarding the quality of the clusters. These are all problems. That is why k-means clusters cannot be used for always. And what you do in that, first you initialize the k cluster centroids, that initially we assume that it is mu1, mu2, mu3, that is what you have done, mu k, and then repeat the distance calculations. That is what you do, and keep on doing the iterative things. Very simple, elegant, faster technique, but the problem is this. So, you have to have a cluster assignment steps and cluster updating steps. These are the 2 steps in the Python modeling, you will do that. So, these are the issues. First you have to initialize, and then you can split the data, but having located the centroid of k cluster, then you can easily assign the data points. So, in comparison, hierarchical clustering is a connectivity based clustering models that groups the data points together that are close to each other based on the measure of similarity or distance. Remember this. So, assumption is that the data points that are close to each other are more similar or related than the data points further away. After that, you create a dendrogram or tree like structure. All of you know dendrites. Dendrogram is basically dendritic like structure, tree like structures, which can give the information of hierarchy, a hierarchical relationship. Individual data points are located at the bottom of the dendrograms, while the largest clusters, which include all the data points, are located at the top. Very simple. Tree has a stem, and the stem has other branches, exactly same way. So, if you want to generate different number of clusters, then you can slice even dendrograms at different heights. Let us do that. Okay, let us see that. This is what is. There are different subjects, right? I have now written that. Let us talk about subjects. Agriculture, biology, physics, computer science, space. So, you look at this. This is taken from yahoo.com. Agriculture can have dairy, crops, forestry, agronomy. Biology can be a botany, cell biology, evolution biology. Physics can be many things. I put only magnetism, relativity. Computer science can be AI. Other courses are HCL also. Space can be craft or missions. So, how many are there? 30. 30 hierarchies are there, right? You can clearly see that if you make it properly. So, what you have done, if you go back to here, it's like a dendrogram, a tree like structure, and individual data points are located at the bottom of this dendrogram, right? Here you see individual ones put at the bottom of the dendrogram, and largest clusters are put at the top. What is that largest cluster? Largest cluster is subjects, that is put at the top. And to generate these different number of clusters, dendrogram can be sliced. You can slice the dendrograms. You can slice here, you can slice here, right? You can slice it up and get a slice means this is one slice. If you want to generate slice here, it is like this, right? This is called slice. So, basically it builds a tree based hierarchical taxonomy from a set of documents. Remember, the basic approach is very simple, recursive applications of partitional clustering. This is basically taking a recursive. Animal can be vertebrate, invertebrate. Vertebrates are fish, reptile, amphibian, okay, mammals. Invertebrates can be worm, insect, crustacean. Then you can divide fish into different categories, reptile in different categories like that. So, that is what it is. So, it is built basically tree based structure, and recursive applications of partitionless clustering is used. Another one, let us talk about all topics. All topics can be anything, right, in the world, but we have decided to make only fashion and sports. And in the sports you are interested in soccer and tennis. Fashion, two companies, Gucci and Lacoste, right. So, you can build these clusters like that, hierarchy clusters. So, hierarchy may be more nature, it can be more natural. Different users might care about different levels of granularity or different kinds of prunings, okay. You can cut it up, use that. So, what is dendrogram then? To give it very perspectives. Okay, dendrogram is basically nothing but cutting the dendrogram in desired level. So, this is basically tree like structures, okay. That is what you should think about it. It is a tree like structures. So, how do you do this dendrogram generation, all these things we will talk about a little bit. Before that, let us talk about what are the two different types of clustering possible, hierarchical clustering possible. One is called agglomerated clustering, agglomerative clustering, other is called divisive clustering. What is agglomerative clustering? It is also known as a bottom up clustering. So, there is a bottom up and top down. So, HAC is basically a bottom up clustering approach, a structure that is more informative than unstructured set of clusters returned by flat clustering. Remember what is flat clustering, right? You do not remember? So, let us go back to flat clustering again, sometime we forget. Basically, flat clustering is nothing but k-means clustering type. It starts with random partitioning and then do it repeatedly. So, what does it say here? If I go back here, HAC, a structure that is more informative than the unstructured set of clusters returned by flat clustering. Flat clustering will give you a set of clusters, but that is less informative than HAC. So, therefore, this clustering algorithm does not require us to pre-specify the number of clusters. You do not require, you can have every data point as one cluster. Bottom up algorithm treats each data as a singleton cluster at the outset, and then successively agglomerate pairs of clusters are found. In comparison, HDC, hierarchical divisive clustering, is a top down approach. This algorithm does not require again to pre-specify number of clusters, but top down clustering requires a method of splitting the clusters that contains whole data. So, here you are basically splitting the top data from the top to bottom, and this is every time this can be done by splitting clusters recursively until we have achieved the singleton clusters, correct. That is what it is. So, you split it up. In case of top down approach, in case of bottom up approach, you do it basically treats every data as a cluster, just like a nanomaterials have a top down and bottom up approach. In bottom up approach, you start with each molecule join one by one and form a nanomaterials. Similarly, here also a bottom up approach, each data point is considered single clusters at the beginning, then successfully we can agglomerate the clusters, pair of clusters. That is why it is called a bottom up approach. Start with the very bottom level, atom level, and then you join them together, agglomerate the spot atoms to form a clusters. But in case of HDC, this is a top down. So, basically you split the cluster that contain the whole data and proceeds by splitting the clusters recursively. Okay, so let us little bit talk about how these hierarchical clusters work. Step 1 of our cluster is basically create each data point as single clusters, correct. Let me go back to the board and talk about that. So, step 1 is very simple in case of hierarchical clustering. Step 1 is basically treat every data. Remember, we are discussing about HAC, okay, agglomerate. Treat every data points, each data point as what? Single cluster, right? That's what is your first job. So, suppose you have data point like this. So, each data point is considered as a cluster, single clusters. Then steps 2, what you do? In steps 2, take two closest data points and merge to form one cluster. So, there will be now n minus 1 clusters, because one you have taken 2 together. So, let me explain you that. Let us take these 2. Okay, let me use different color. Red is better. Let us take these 2. These 2 are closest data points, so merge them into one clusters. Okay. So, that is what it is. That is the steps 2. What is step 3? Step 3 is very simple. Again, take two closest clusters. Two closest clusters and merge them together to form another cluster. What is in terms of that? So, I will do again that. Let us talk about these 2. That is the step 3, correct. So, very easy to understand, not very difficult. The step 4 is what? Repeat step 3. Basically, what you are doing is repeating step 2 again and again. Repeat step 3 until only one cluster is left. Right, that is what you do. So, what you do is very simple here then. So, first we remove this. We have done the repetition of step 3, so that you have only one cluster estimate, only one data point estimate, right. So, then we are done almost. So, you have one more step. What is that step? Step 5. Step 5 is the last step. What is the step 5? Once all the cluster combine into big cluster, develop the dendrogram. Once all clusters are combined, develop a dendrogram. I discussed about dendrogram. It is nothing but a dendritic structure. So, these are the 5 steps you should do, not more than that, you can clearly see. So, these 5 steps are required. So, you have to develop a dendrogram, and dendrogram is something which is giving you the nature of clusters, right. We have discussed about dendrograms quite a lot. So, few more important things we need to talk about it. What is the measure of distance between the clusters? Okay. The closest distance between two points is basically what is called the measure of distance. There are various types of ways to means to calculate the distances. Okay. So, you could clearly see now here how we measure distance by measuring the closest distance between these 2 points, correct. That is what we are doing, but there are many ways of determining the distances possible. Let us talk about that, because these are the algorithms. First one is known as a single lineage. So, we will discuss about that part little bit. So, I remove this, hope you have taken down whatever written the different steps. So, how to measure distance, because that is what it is. So, there are different kinds of ways of distance. First one is known as a single cluster, single lineage, sorry. What is it? If you, this is the shortest distance between the closest data points of the clusters. Let us talk about this picture. So, let us talk about this. This one clusters, these are other clusters. So, you can clearly see the distance of this point and this point. This is the closest distance or shortest distance. So, it talks about shortest distance between the closest points of a cluster. Okay. That is what we have done. We consider this point and this point, these are the closest points, and find the distance between. This is a single lineage, one link only. That is why I will get single lineage distance. That is what is more important and widely used. Second one is what is known as a complete linkage. Sorry, this is not a lineage, linkage. I am making a mistake. Linkage. Then you can have a complete linkage, second one. What is it? It is the farthest distance between the 2 points. So, farthest distance. So, if I have to draw the same thing here, this is one cluster, then another clusters. This is talking about the farthest distance, right. So, this point and this point, that is what it is. Farthest distance between the 2 points of the 2 different clusters. It is one of the very popular linkage methods. So, remember what we are doing when you want to form this hierarchical clusters. We can either do a single linkage or further distant linkage. That means they are part of 2 different hierarchies in the dendron structure. You can have also much more complex things possible. So, let us talk about that. You can have centroid linkage also possible, centroid. That is very simple, what we discussed already. So, let me just draw it. So, this is the centroid, let us say, of this cluster. This is centroid of these clusters. This distance what is called centroid linkage. So, these are a different linkage we used in the to get the dendron. Okay. Am I clear? So, by using these different kinds of linkage, one can find the dendrons. Okay. Remember, the clustering was done as we discussed already, considering the each point as a cluster and do that. So, HSC basically works on that. So, once you have done that, then you can easily form the dendron nicely, you can easily form the dendron structures. That is the key thing about in hierarchical clusters. So, as you know, the hierarchical HSC starts with each dot as a, this is a dot basically, not dot, in a separate cluster, and then repeatedly join the closest pair. And history of merging, how we are merging the forms from the tree or the dendron structures in the hierarchy. So, we have talked about it, both the top down and the bottom up approach. Again I am telling you, in top down, which is nothing but divisive approach, you partition the data into two groups first, then you do it again and again, right. Just like in nanometal synthesis, you take a chalk, break into pieces till you achieve the nanomaterial. Same thing you do here. Okay, you have the whole data, partition into two groups, and bottom up approach basically starts with every points in one cluster, and then you merge actually the closest data points. So, remember these aspects. Well, I just wanted to tell you the mechanism of distance to finish it up again. So, normally we use Euclidean distance, but you have already seen we can use Manhattan, we can use Minsky, or we can use even quadratic, chi square, many other distance type matrices in the literature. So, what you have learned in today's lecture is quite a lot, right. You learned the K-means algorithm and hierarchical algorithm. Now, if I go back different kinds of algorithms, yes. So, we have discussed about centroid based algorithms, connective based algorithms. Density has similarity like centroid based algorithms. So, basically it finds groups based on the density of data points. Density is number, nothing, a number density. How many data points are there per unit area, per unit volume, that is what is used. That is much easy to measure, right. You can count and find out the volume, find out the area and do that. So, what needs to be done in the next class is basically this distribution based clustering. Okay, we will talk about a little bit in 5-10 minutes in the next lecture about distribution based clustering, and then we move ahead. So, with this let me stop here. I hope you will enjoy this kind of descriptions of mathematics and the geometrical things to understand the whole clustering. Thank you.